before we continue?
دكتور عندي سؤال.
Yes.
No, no.
Yes, tell me.
Can you go back to the original figure, please?
Yeah.
Okay, دكتور على الصورة على الشمال
No.
هيدي من بعد ما قسمنا الفورسز.
Yes.
We did the resultant تبع دي we elongated the line of action وطلع it intersects with the 400 Newton force, صح؟
دي صح.
Okay, we did the same thing for AX and AY and we elongated it. We did the resultant to كمان بيطلع
Yeah.
إنه it intersects مع 400. مش هيك
Yes,
عرفنا إنه
exactly.
3
Yes, because when you have a
three-way-
three-force
three-force
member, yes, when you have a three-force member, the three forces should pass by 1 point. And since you know the two first forces, and you know that 400 Newton is horizontal, and from the two force members, you determined that the force passing by B should do an angle of 45. This will allow you to determine what is the intersection point between the two. And once you find the intersection point between the two, by looking at ABC, since it is a three-force member, then the force at A should pass by the same point. Okay?
دكتور كيف عرفت إنه ABC 3-force member؟
لأنه شو هن الفورسز acting on ABC؟ You have a force at A اللي هي أول شيء you have هن قالوا لك the weight of members is negligible, so you don't have a weight. You have a force applied at A force applied at B, and a force applied at C, and you don't have couple moments. يعني شو هن two conditions? The first one, no couple moment acting on the structure. Second one, to have a three force members, forces should only be applied at 3 points, not more. So A, B, C, you have only forces at A, B, and C, and no couple acting on it. So it's a three-force member.
Okay, thank you, doctor.
Any other question? Yes, Karen, of course, we have equilibrium conditions. Okay? So whenever you have a structure supported and you have supports, then you have equilibrium conditions. Okay? Let us continue. Now, equilibrium in 3D. So as in 2D, the first step in solving any equilibrium problem is to draw the free body diagram. But in order to know how to draw the free body diagram in 3 dimensions, we should know what is the type of supports and what types of reactions I can produce. Okay? So in 3D, it is a little bit more complex than 2D. But we have several common things. So first, for a cable, as usual, the cable can only sustain tension. So whenever I have a cable, the action of the cable on any part will be directed towards the cable. So it's one unknown when I have a cable. If I have a smooth surface support, it's similar to 2D. I will have only a force perpendicular to contact. Now, of course, also if I have a roller, also for a roller, I have a force perpendicular to contact. So until now, these are common with 2D connections. Now, other types of 3D support. The first one is ball and socket joint. So for the ball and socket joint, it's like if you want, you can take as example for let's say مثل يعني إذا بدكم مثل فيتاس السيارة قبل ما تحركوه يعني if you are not translating it, you are just rotating it around one point. This is a ball and socket joint. Okay, so you cannot displace it in X, Y, and Z because it is fixed to this point. But what can you do? And always, when you want to determine the reaction, think about what I can do. If I can do something, this means that this support is developing a reaction to oppose motion. So can I translate this point in X, Y, or Z? No, I cannot. So my ball and socket joint will develop reaction forces in X, Y, and Z. Now, can I rotate it? Yes, I can rotate it in any direction I want. Okay, you can rotate it around this point in any direction, in X, in Y, or in Z. This is why it will not develop any reaction couple. Okay, so here when you see this symbol is for ball and socket joint, and you should know also the name. So if they tell you I have a ball and socket joint connection, then you should know that ball and socket will not allow translation in any of the three directions. It will only allow rotation. Okay. Another type of connections in 3D is a single journal bearing. For single journal bearing, in this case, what will happen? If you look at this figure, for example, you can rotate your bar in this direction along an axis along the line of the bar. Okay, so therefore this reaction will not develop a moment in this direction. But try, can you rotate it like this, for example? No, you cannot rotate it in this direction. Why? Because you have here a support here that will oppose rotation in this way. Okay, and also you cannot rotate it like this. So you can only rotate this bar around its axis. This is why you will have two reaction couples, one in Z, one in X. So these two couples are perpendicular to the axis of the rod. Since I can only have a couple rotation along the axis of the rod. So no reaction along this direction, but I have a reaction along these two. Now, concerning the force, can I translate from my figure, can I translate the rod along this direction? It seems yes. Okay, so because here you have like a hole, you can translate if they don't mention any additional information. If they don't say you have a thrust, or if they don't say that we are blocking translation, then you can move your rod in this direction. So you don't have a force developed along the axis of the rod, but you cannot move it up and you cannot move it in this way. So your reaction will develop forces also in these directions. So in total, a single journal bearing will develop two forces and two couple moments in direction perpendicular to the rod. Okay, so here you have four unknowns in this case. Now, another possibility is a single journal bearing but with square shaft. If I have square shaft, what is the additional constraint I will add? Look, if I have a square shaft, can I rotate the shaft around this or around its axis? Try to imagine it. Can you rotate a square shaft about
No.
its axis? No, because here you have that here, due to the support form of a square, you cannot rotate the rod inside the bearing. Therefore, in addition to the four reactions developed by a single journal bearing with a circular shaft, you should add to it the constraint that I cannot rotate also around the axis of the rod. So what should I add to these four reactions? I should add the moment couple reaction. The only freedom of motion I can have here is translation along the axis of the rod. So translation along y. This is why I will not have reaction of Fy, but I will have all other types of reaction. I will have Fx, Fz, and I will have Mx, My, and Mz, since I am not able to rotate in any direction. Okay. Now, other types of supports in 3 dimensions. If they say single thrust bearing, okay, so when they say thrust bearing, it's like we have a locking effect. The locking effect will prevent translation. So when they say thrust, okay, this means that I have like a locking effect inside that will not allow translation, but I can just rotate. Okay, so when they tell you it's a single thrust bearing, then you can say the only freedom of motion is rotation about the axis of the rod, and I cannot translate it due to the locking effect. Now, other types of reaction, single smooth spin in 3D. If I have a single smooth spin, when they say smooth, this means that I can rotate. Okay, If it was rough also, then I cannot do anything. So here I have, since it's smooth, I can rotate around this axis. So for a single smooth pin, I can do only rotation about this axis, and I cannot do anything else. I cannot translate in any direction. So I cannot move like this, I cannot move like this. So I will have development of reactions in X, in Y, and in Z. So as you can see here, you have Fx, Fy, and Fz. You want me to zoom a little bit the figure, or are you seeing clearly?
It's clear.
Okay. So, so here I can just do rotation. So I will have Fx, Fy, Fz, and I will have My, Mz. I will only not have a couple in this direction because I can rotate around this direction. Okay. Now, another type of connections is single hinge. Okay. So a single hinge is like the connection used for doors. Okay. So for a door, you can look, if you look at the corner of the door, you can see these types of connections. These connections will allow only rotation. They, like smooth pins, they will allow rotation only about this axis, and they will prevent any translation and any rotation different than rotation about this axis. This is why also a single hinge will develop 5 constraints, 3 forces, and 2 couples. We only have freedom of rotation about this axis, so no couple moment along this axis. Okay. And finally, the fixity. So the fixity will not allow me to do anything. It's like 3D, like 2D. Okay. In 2D, a fixity develops 3 types of reaction because it will not allow translation and will not allow rotation. But in 3D, it will develop 6 reactions because I cannot move in any direction. So I have 3 force constraint. And I cannot rotate also in any direction, so I will have 5 moment couple constraints. So this is the maximum number of reactions I can have. The fixity will represent 6 unknowns. This is why, in general, if we have a fixity, one fixity is enough to support a structure. I don't need any other type of support. Any question on types of supports in 3D? Okay. Now, once we have determined what are the different types of support, now we will move to application of equilibrium in 3D. So in 3D, we know that the equilibrium of a rigid body involves 2 vectorial equations. Sum of forces equals 0 and sum of moment equals to 0. And each vectorial equation in 3D will give me 3 equations. So I have 3 forces equations and 3 moment equations. So I will end up with 6 equations with 6 unknowns. Okay. Now, sometimes equilibrium is not possible. Okay. Or sometimes equilibrium is only possible in particular cases. What do I mean by this? So if I don't select properly my support, I might end up with cases that cannot always be in equilibrium. So some bodies may have more support than are required for equilibrium, whereas others may not have enough supports, or the supports can be arranged in a manner that would cause the body to collapse. What do we mean by this? I will give you a simple example in 2D first. Okay? If you have this structure in 2D and you put 2 rollers, these 2 rollers are able to maintain equilibrium in any condition, in any type of loading I put on the beam. Okay, guys, sorry, time is over, so I will continue next time, okay? Because someone should leave because you have other class, okay? So I will continue the explanation next time. We will start from this slide. Any
Thank you,
questions?
Doc.
Thank you.
Welcome, guys. Okay, bye.
Thank you, Doc.